Section: Introduction. In this section, we discuss the concept of self-adaptive large language models, LLMs, which could greatly enhance artificial intelligence by allowing models to adjust to different tasks and changing contexts in real time. We recognize that while compositionality and scalability are essential for effective adaptation, current training methods for LLMs struggle to achieve both simultaneously. Our research aims to provide an innovative solution to bridge these gaps. Traditionally, post-training for LLMs has focused on optimizing a model for various capabilities in a single, extensive training session. While this one-shot, fine-tuning approach is straightforward, it is challenging to implement effectively. For example, post-training requires significant resources, leading to high computational costs and long training times. Additionally, expanding the data often results in performance trade-offs, making it hard to avoid overfitting and task interference. In contrast, self-adaptive models present a more flexible and efficient method. Instead of training an LLM for all tasks at once, we can develop expert modules offline and add them to the base LLM as needed. This allows the model to adjust its behavior based on the specific task without constant retuning. The modularity of this approach also supports continual learning, enabling the model to acquire new skills over time without losing previously learned information. Moreover, self-adaptive LLMs reflect a principle found in neuroscience, where the brain activates specific areas based on the task and reconfigures itself as needed. We propose that the first step towards self-adaptive LLMs involves creating specialized expert modules, fine-tuned using methods like low-rank adaptation, LoRA. These modules can be combined dynamically during runtime based on task requirements, managed efficiently through systems similar to Mixture of Experts, MO. However, we face several challenges in making this approach scalable and compositional. First, fine-tuning LLMs to create multiple expert modules increases the number of parameters that need training. Even with efficient methods like LoRA, the total size of these modules can grow quickly, raising storage and computational needs. Second, these expert modules can easily overfit, especially when trained on smaller datasets. Third, the flexible combination of these modules presents unresolved challenges that remain open research questions. To address these issues, we introduce singular value fine-tuning, SVF, a new parameter-efficient fine-tuning method that focuses on tuning only the singular values in the model's weight matrices. This targeted approach helps reduce overfitting risks, lowers computational demands, and supports compositionality. We demonstrate that SVF allows us to efficiently create effective domain-specific expert vectors by training on narrow datasets with reinforcement learning, optimizing performance on specific tasks. Next, we present our full transformer squared framework, which enhances LLMs based on self-adaptation principles. When given a prompt from an unknown task, transformer squared uses a two-pass inference mechanism. In the first pass, it executes the model and observes its behavior, gathering information to identify the necessary skills for the current problem. In the second pass, it uses this information to combine available expert vectors and adjust the base weights of the LLM to fit the test time conditions. We design 3 adaptation strategies within transformer squared, which we show lead to improved performance as access to test time conditions increases. We evaluate SVF and the transformer squared framework through extensive experiments across various LLMs and tasks. Our results indicate that SVF consistently outperforms traditional fine-tuning methods like LoRA, using significantly fewer parameters. Furthermore, transformer squared enhances performance even in entirely new applications, such as visual question answering. In summary, our key contributions include the development of transformer squared as a self-adaptation framework for LLMs, the introduction of SVF as a novel fine-tuning method that produces compact expert vectors, and the implementation of 3 adaptation strategies to effectively utilize SVF-trained experts for different needs and scenarios. Section Summary. In this section, we introduce self-adaptive large language models, LLMs, that can dynamically adjust to various tasks using specialized expert modules, addressing the limitations of traditional one-shot fine-tuning methods. We propose singular value fine-tuning, SVF, for efficient parameter tuning and present the transformer squared framework, which enhances LLM performance by combining expert vectors based on real-time task demands, ultimately enabling scalable and flexible model adaptation. Section: Related Works. In this section, we discuss self-adaptive large language models, LLMs, which we define as either a group of LLMs or a single LLM that can assess and adjust its behavior based on changes in its environment or internal state without needing outside help. We can look at this adaptation from two angles: a macro view, where multiple LLMs work together or compete, and a micro view, where a single LLM adapts to specialize in various tasks. From the macro view, we see that the system directs questions to LLMs that have specific expertise, prioritizing responses from these expert models to improve accuracy and optimize for specific tasks. This collaboration can happen in different ways, such as having multiple LLMs take on different roles, engaging in discussions, or using carefully designed prompts to combine knowledge and skills. The better each LLM specializes and adapts, the better the overall performance of the group. In this paper, we focus on the microview of self-adaptive LLMs. Here, mixture of experts, MO, plays a vital role. In MO systems, inputs are dynamically sent to a select group of specialized modules that hold domain-specific knowledge. To speed up processing, researchers have developed sparsely activated MO, where only a few experts are chosen for each input. While we can loosely consider transformer models as a type of MO, there are key differences. In traditional MO, adaptation happens at the token level, while transformer models use a sample-level selection method. Additionally, traditional expert modules are either trained from scratch or adapted from dense models without a specific loss function to ensure they specialize. In contrast, transformer models train expert vectors using reinforcement learning to gain true domain expertise. We also explore low-rank adaptation methods like LoRA, which frees the original model's parameters and adds small, trainable low-rank matrices for specific tasks. This approach significantly reduces computational and memory costs while maintaining performance similar to full fine-tuning. Inspired by LoRA, various modifications have emerged. However, transformer models do not use low-rank matrices. Instead, they scale the singular vectors of the original parameter matrix. Singular value decomposition, SVD, is increasingly used as a guiding principle for parameter-efficient fine-tuning in LLMs. For instance, we can break down a weight matrix and use the smaller singular components, which are often associated with noise, to initialize low-rank matrices for LoRA fine-tuning. Similarly, SVD can approximate an original weight matrix using the top singular vectors, which correspond to the highest singular values. We then add a small trainable matrix to adjust the values within this top subspace. However, a downside of this method is that focusing only on the top singular components can lead to the loss of important information, especially when the distribution of singular values is not heavily skewed. We note that there is related work that introduces various sparsification methods using SVD of weights, but it does not focus on self-adaptive LLMs or use reinforcement learning to improve learning efficiency. In our methods section, we provide some preliminaries. SVD gives us a basic understanding of matrix multiplication. In neural networks, we can break down a weight matrix into 3 parts, resulting in semi-orthogonal matrices and a set of singular values arranged in descending order. This allows us to express the operation of applying the weight matrix to an input as a sum of independent terms, where each singular component processes the input separately, contributing orthogonally to the output. We also discuss the cross-entropy method, GEM, a Monte Carlo technique for optimization. GEM minimizes the divergence between two probability distributions by generating samples, evaluating them, and updating the distribution based on the best performing samples. Typically, we start with a diagonal multivariate Gaussian distribution and refine it by estimating the mean and standard deviation of the top samples until we meet a stopping criterion. We will illustrate a complete GEM step in the following pseudocode. Section Summary. In this section, we define self-adaptive LLMs as models that can autonomously adjust their behavior based on environmental changes, focusing on both macro and micro perspectives. We emphasize the microview, highlighting the role of mixture of experts, MO, in enabling dynamic routing to specialized modules, and discuss the use of singular value decomposition, SVD, for efficient fine-tuning while noting its limitations. Section. #MATH184 #TRANSFORMER. In this section, we outline the construction of transformer squared, which involves two main steps, as illustrated in the accompanying figure. First, we introduce singular value fine-tuning, SVF, a technique that helps us learn compact and compositional expert vectors using reinforcement learning, RL, based on the singular value decomposition, SVD, of the base model's weights. Next, we present three adaptation strategies within transformer squared, inspired by distinct principles, that combine the SVF-trained expert vectors during inference. SVF is crucial for transformer squared, providing an efficient way to fine-tune and adapt models. Traditional fine-tuning methods often modify weight matrices to add new capabilities. However, large-scale transformers already contain a wealth of knowledge from their pre-training. Instead of adding features, we focus on making existing capabilities more expressible. For any weight matrix, SVF learns a simple vector that modifies each singular component independently, resulting in a new weight matrix. This approach has several advantages. 1. Fewer parameters. By learning only a vector for each weight matrix, we achieve efficient fine-tuning with significantly fewer parameters compared to methods like LoRA, which require more learnable parameters. 2. High compositionality. Decomposing weights into independent components allows for highly composable and interpretable learned vectors, enabling various adaptation possibilities. In contrast, LoRA methods lack this flexibility. 3. Effective regularization. Modifying the magnitude of existing singular components provides a principled form of regularization, allowing us to fine-tune models with limited data without risking overfitting. We also employ RL to train a set of SVF vectors to fine-tune any language model, optimizing directly for task performance. We use the reinforce algorithm, assigning rewards based on the correctness of generated answers. To stabilize the training, we add a penalty for deviating from the original model's behavior. Our approach to self-adaptation focuses on the inference stage of LLMs, where we implement a two-pass adaptation strategy using multiple sets of SVF-trained expert vectors. In the first pass, we derive a new vector tailored to the input prompt, which is then used in the second pass to generate a response. We propose three methods to produce this adapted vector during the first inference pass. A. Prompt engineering. We create an adaptation prompt to categorize the input, selecting the corresponding expert vector based on the model's response. B. Classification expert. We fine-tune the base LLM to improve task identification, using a dataset from the SVF training tasks to create a classification expert that helps select the appropriate vector. C. Few-shot adaptation. We leverage additional task information by interpolating between learned SVF vectors based on performance on few-shot prompts, optimizing the adapted vector without increasing prompt length. Overall, our methods ensure seamless integration of expert vectors and adaptation strategies, enhancing the model's ability to respond effectively to various tasks. Section Summary. In this section, we present the construction of transformer squared, which involves singular value fine-tuning, SVF, for efficient learning of expert vectors and three adaptation strategies that dynamically combine these vectors during inference. We emphasize that SVF enables effective fine-tuning with minimal parameters and high compositionality, allowing for self-adaptive capabilities in large language models without the need for extensive datasets. Section. Experiments. In this section, we extensively evaluate transformer squared on various tasks and models to achieve three main goals. First, to assess the efficiency and effectiveness of the SVF. Second, to demonstrate self-adaptiveness through our 3 proposed adaptation strategies. And third, to conduct detailed analyses and ablation studies to better understand our new framework's properties. For our experimental setups, we validate the generality of transformer squared by using 3 pre-trained large language models, LLMs, of different families and sizes: Llama 3 to 8B Instruct, Mistral 7B Instruct v0.3, and Llama 3 to 70B Instruct. For each model, we create 3 sets of SVF-trained vectors to optimize performance on the GSM-8K, MBPP Pro, and ARC-Easy tasks. Additionally, we train a set of vectors for Llama 3 to 8B Instruct as the language backbone for text VQA to evaluate SVF's applicability in the vision language modeling domain. We present SVF's main learning curves for these tasks in a figure. Lastly, we test the full transformer squared adaptation framework on 4 new tasks: Math, Human Evil, ARC Challenge, and OKVQA. In all our adaptation experiments, we focus on experts obtained in pure language settings, assessing their applicability even in the vision domain. More details and a summary of the hyperparameters used can be found in the appendix. Regarding our experimental results, we present the performance of SVF after training on each task with the Llama 3 to 8B Instruct, Mistral 7B Instruct v0.3, and Llama 3 to 70B Instruct base models in a table. We find that SVF consistently provides significant performance improvements across nearly all tasks and models, while LoRA experts show smaller gains and occasional performance drops. Notably, LoRA experts trained with next token prediction perform less effectively than those trained with reinforcement learning when compared to SVF. This trend also holds in the vision language domain, where fine-tuning LLAMA3 LLAVA Next 8B with SVF enhances performance by over 39%. To ensure fair comparisons, we conduct extensive ablations of both our model and the LoRA baseline, considering different architectures and optimization objectives in the appendix. Importantly, training SVF requires significantly fewer resources, using less than 10% of the training parameters needed for our LoRA implementation. For adaptation performance, we evaluate the self-adaptation capability of transformer squared using the SVF-trained vectors on unseen tasks. We compare this with LoRA by recording its performance using all checkpoints from the training tasks and reporting only the highest performance for each test task. Our results show that all transformer squared adaptation strategies improve performance across all tasks for the Llama 3 to 8B Instruct base model, and in at least 2 out of 3 tasks for both MISTRAL 7B Instruct v0.3 and Llama 3 to 70B Instruct. In contrast, the best-performing LoRAs provide only marginal improvements on the ARC Challenge task and significantly worsen performance on Math and Human Evil. This suggests that LoRA's parameterization and optimization may be particularly prone to overfitting, especially with the smaller datasets related to Math and Human Evil. We observe a similar pattern in the OKVQA task, where the base LLAMA3 LLAVA Next 8B model only improves after applying transformer squared. Here, transformer squared adapts using expert vectors from GSM-8K, MBPP Pro, and ARC-Easy, highlighting its flexibility in transferring knowledge from language tasks to unrelated vision problems. When comparing our 3 proposed adaptation strategies, we notice a clear trend. More complex strategies with additional information about the test conditions lead to better self-adaptation. Specifically, transformer squared with few-shot self-adaptation consistently scores the highest, showing significant improvements across all tested settings, except for Llama 3 to 70B Instruct on Math, where we only tuned half of the layers due to limited GPU resources. This trend indicates that providing additional or varied information is highly beneficial for our framework, suggesting that transformer squared could enable foundation models to continuously enhance their performance in real-world applications. Finally, we report the inference time required by the prompt adaptation strategy of transformer squared, detailing the time taken for both the first and second passes. While the second pass time reflects the duration for solving the problems, the first pass time is for self-adaptation. Although the additional inference pass may seem to double the overall runtime, it primarily depends on the number of tokens generated. In our experiments, this is proportional to the length of the input. The cost ratio for the ARC challenge is high due to its single-choice problems, making the second pass also proportional to the input length. Generally, we believe this ratio is more aligned with those of math and human evil. Section Summary. In this section, we evaluate transformer squared across various tasks and models to assess the efficiency of SVF, demonstrate self-adaptiveness through proposed strategies, and conduct detailed analyses. Our experiments show that SVF consistently outperforms LoRA in performance and resource efficiency, while our adaptation strategies enhance performance on unseen tasks, highlighting the framework's flexibility and potential for continual improvement in diverse settings. Section: Analysis. In this section, we analyze and discuss the properties of our adaptation strategies, providing extensions and further discussion in the appendix. Analysis 1. Job dispatching accuracy. We present confusion matrices for our classification-based adaptation strategies. These results confirm that our strategies effectively match prompts with experts trained in similar areas, as shown by the high diagonal values. Additionally, the results from Llama 3 to 8b instruct and MISTRAL 7b instruct v0.3 indicate that using classification experts leads to better accuracy compared to standard prompt engineering. While this might explain the superior performance of our self-adaptation strategy, we recognize that domain similarity may not be the only factor in selecting the best expert for each task. We believe there are many unexplored avenues for future work, such as using past expert performance or analyzing token-level data to enhance our framework scalability. Analysis 2. Training tasks adaptation contribution. We show the normalized adaptive coefficients that connect our SVF vectors learned through GEM for Llama 3 to 8b instruct and MISTRAL 7b instruct v0.3 across unseen tasks. We find that expert vectors from training tasks with similar topics to the unseen tasks often contribute the most to the adaptive weights. However, the math task stands out as an exception, where the adaptive coefficient for the expert from GSM-8K training is the lowest in both models. We think this reflects the different nature of math competition problems compared to the grade school problems in GSM-8K, as math questions are generally more challenging and rely heavily on logical reasoning. We also observe that the different vectors contribute more evenly to adaptation in the Llama model, suggesting it can benefit from self-adaptation without relying on specific skills as much as Mistral. However, applying the adaptive coefficients uniformly is not a one-size-fits-all solution, as seen in different model and task combinations. Analysis 3. Ablation studies. We first compare the performance of SVF across different modules. Under consistent conditions, both individual MLP and attention updates enhance performance, with MLP updates showing more significant improvements. Updating both types simultaneously yields even better results. We also examine the impact of different objective functions, comparing the RL objective with next token prediction loss. Our results show that RL leads to clear performance gains, while next token prediction can actually hinder performance, highlighting RL's effectiveness in task-specific fine-tuning. Lastly, we evaluate LoRA using the RL objective and find a significant performance gap, mainly due to the instability of the LoRA training process, despite testing various learning rates. Analysis 4. Cross-model compatibility. We explore the potential of our self-adaptation framework across different LLMs, specifically whether the SVF expert vectors from Llama 3 to 8b instruct can benefit MISTRAL 7b instruct v0.3. Our findings reveal that positive transfer occurs between the two models, with improvements in 2 out of 3 tasks. These enhancements are attributed to the structured nature of the SVF parameterization, as shuffling the SVF vectors before applying them to the Mistral model consistently reduces performance. Additionally, Performing few-shot adaptation using SVF vectors from both models further boosts MISTRAL7B instruct v0.3 feet S performance, even surpassing the best score from adapting it with all SVF vectors in the ARC challenge task. While these results are encouraging, we note that the compatibility we observed may be linked to the similarities in the architectures of the two LLMs. Whether similar transfer can be achieved with models of different scales remains an open question, which could lead to new insights in recycling task-specific skills for larger models, with significant implications for accessibility and sustainability.